Hello, everyone. I'm Marco Slot. I'm a software engineer at Crunchy Data, and I'm going to be talking about data-intensive Postgres, 3 ways to scale, or rather 3 different types of workloads that you might struggle with on Postgres if you have a data-intensive application. Basically, the word data-intensive, I think, comes from this book, Designing Data-Intensive Applications by Martin Kleppmann, and he gives a good definition where we call an application data-intensive if data is its primary challenge, either the quantity, the complexity, or the speed at which it's changing. It's a pretty good definition. Another term that people have used is the 3 V's of data. I find it a bit easier to remember. It's the volume, the velocity, and the variety of the data can make a data problem hard. So how much data am I storing, ingesting, accessing? That's the volume. How quickly does it change? How fast does the data need to go through the system? The velocity, and how many different types of data and queries and relationships and distributions. That's the variety of the data. And so when these are high, you kind of have a data-intensive application, and those are always a little bit tricky to deal with. So we're going to look at a few different types of workloads that people often run on Postgres and how you can essentially deal with them if they become data intensive. And not all applications have a tendency to become data intensive. If you're running you're just keeping the grades for a single school in a database, that's not going to be a data intensive application anytime soon. Not all data-intensive applications use Postgres, like training machine learning models at scale. But some applications use Postgres and tend to collect a lot of data or ingest a lot of data. For example, software as a service applications, they can quickly add more customers that bring in more data into the system. Time series scenarios, they have this large stream of data and want to do analytics on it. And business intelligence, where we take all the data from the company and try to make data-driven decisions. So some of these applications, they tend to get to a point where they are data-intensive, where there's a lot of load, a lot of variety, velocity, volume, and then things get hard. And that brings us to the age-old question of how do you scale Postgres? And people who know me know that I only have one answer to this question. It depends. Really depends on the characteristics of the workload. So scalability and performance are these kind of multifaceted umbrella terms almost. So performance has a few different facets. For example, response time is the most obvious one. How long does it take between me clicking a button and the application doing something? But there's also the timeliness and quality of data. So how long does it take between an event happening and it showing up in the application? If the system is performing poorly, it doesn't scale, it might start taking longer, or maybe I'm missing some of my data. And systems builders also use this notion of goodput, which is the work that the application or the database does, which is actually useful. Because you could have a database that's processing lots of data really quickly to answer all sorts of queries, but maybe the users feel like they're waiting so long that they switch to another screen and they never see the result of the query. So that's high throughput, but not good put. And it's important to get good put. So under high load, obviously things get slower, partly because the CPU and the disk, they might be busy. But there can also be these secondary effects where, for example, in Postgres, you have auto vacuum, where if the auto vacuum process falls behind, the table gets bigger and more bloated. And then scans on that table take longer, but also use more resources, putting more pressure on the system. So you can get into these spirals that can be very nasty to get out of. So to deal with this, one thing we should always do is tuning, but it doesn't always help as much as we'd like. The really important things to do is in the design of the application and the database, because we need really good data structures. We need to use the right indexes, materialized views, good table design. Another thing we might need to do is take good advantage of parallelism or scale out using multiple machines. And a third, often forgotten aspect is application co-design. Like, you should design your application in a way that allows your database to scale. For example, if you need to insert a lot of data into your database, it's best not to do single row inserts because every insert has some overhead. Every commit has some overhead. It's also best not to do multi-row inserts. They just take a lot of memory. It's better to do copy. Copy is very efficient, can ingest a lot of data per second. So it's important to consider the characteristics of the workload to decide like which one of these things can I do to kind of help me deal with my data problem. So if I have building a software as a service, I think it's a great thing both for software builders and for software users, because customers, like, they don't have to install stuff on their laptops or their employees' laptops. They just sign up, and usually through single sign-on, immediately everyone in the company can start using it. And of course, for the vendor, that's great, easy to onboard new customers. And as a result, software as a service sometimes grows pretty quickly, and that can put some pressure on the database. And one of the subtle issues in that is that you get a pretty large working set, which means that the part of the data that sits in memory. So if you think of a news website, like, everyone is hitting the front page and the first article. So as long as that's cached on a lot of servers, things will be fast. But in a multi-tenant application, everyone is looking at their own data. So if you want to cache all of that in memory, it might actually be too much to do that. Also, by the time a software as a service becomes successful, it probably solves some kind of hard problem, and that comes with a lot of complexity. So we're talking about scaling really complex data models. And usually there's also a mixture between very big and a lot of very small tenants that have different hardware requirements, and they pay different amounts of money as well, so you kind of need to adjust to that. But most workloads also have some redeeming quality, something that makes it a little bit easier to deal with. For multi-tenant apps, that's basically the fact that most of the operations, sometimes all of the operations, are scoped to a single tenant. And what that means is that software as a service is supremely suitable for sharding. As long as I put all of the data for a specific tenant on the same machine, all the operations for that tenant can be handled by that machine, and for a different tenant can be handled by a different machine. And there's actually many different ways to shard a multi-tenant app. The sort of most classical one, perhaps the most commonly used, I create a virtual machine per tenant. Like, I can go to my cloud provider, use their managed Postgres service, or manage my own machines. But like, if I have a product that with large tenants with, let's say, pricey contracts, that's can be an attractive thing to do. I get dedicated resources for every tenant. They're very well isolated from each other. If my application has some kind of SQL injection bug, then one tenant cannot get access to another tenant very easily. So it has a lot of benefits. But if I have millions of tenants, like, this is a very bad idea to be managing millions of virtual machines and millions of Postgres servers. So there's these kind of steps down where the overhead per tenant goes down, and you can handle more tenants on the same amount of hardware, but you don't get as sort of comprehensive isolation benefits. So one example is there's the serverless system where you basically, a lot of Postgres servers share the same VM, and they can resize a bit more dynamically. You could have a database per tenant and spread the databases across servers. You could have a schema per tenant, spread the schemas across servers. This is something Citus can do very nicely. Or you could have a row set per tenant where there's a shared set of tables, and all the data is in that set of tables. And for each table, you have a tenant identifier column that shows you that that's the data for a particular tenant. And then Citus could make sure that all the data for the same tenant is in the same machine, such that even foreign keys and joins, they can all get handled by the same machine. So each of these can scale, but with some different characteristics. as I said, like if you have a really large number of tenants, millions, like it's best to go towards row set per tenant because there's basically no overhead per tenant. It's also great for administration, like you can share everything, the configs, the set of tables. If you add a column, you can do it at once for all the tenants. You can query across tenants, so that's nice. But if you have much smaller number of tenants and isolation is really important, and you need to be able to connect your database server to their network, for example, like those are very much more specific requirements, then maybe VM per tenant is more attractive, or one of the ones in between. Now, in each of these, if you have a large tenant, you can typically isolate it to its own machine. So they can all deal with a mixture of small and large tenants. So yeah, as I said, row set is the most efficient and VM is the most kind of coarse, but the most isolated, but also the most administrative overhead. And in between, there's good option as well. My personal favorite is the schema-based sharding in Citus, because there's not a lot of extra things you need to do to make it work. You just create a Postgres schema per tenant. You could do the same thing on Postgres. And then Citus can distribute those schemas across multiple nodes if you need to scale out. And scale out is a pretty good cure for these types of applications, because if you get into these spirals, for example, where auto vacuum doesn't keep up, you can simply add more auto vacuum processes by adding more machines. So another challenging type of application is time series. And particularly time series dashboards that have a lot of users and kind of show real-time information, maybe within a few minutes or sometimes seconds. And then there's this big stream of time series data, of observations, of events that tends to grow over time that you need to deal with and you need to do your analytics on. So this is challenging for a number of reasons. One is large and often growing data volume. You have a pretty short time to insights that you want, where maybe in less than 5 minutes from an event happening, you want to be able to show it on the dashboard, maybe in less than 1 minute. There can be many concurrent queries from different users, so you want to be able to handle those quickly and efficiently. And there's usually many dimensions for aggregation and filtering. Like if these are devices producing sensor data, there can be different types of sensor readings from different types of devices in different locations. The time is always a dimension, can be different time ranges, how much in an hour, how much in a day. And so that adds to the complexity. The redeeming quality is usually the queries are relatively simple aggregations and filters. And they're usually kind of predictable. They're just the things that the dashboard does to show charts. And the queries are mostly on recent data. But still, it's a difficult problem. And here, it's much more important to have good data structures than to, for example, scale out. Those scale out can also help for very large scale scenarios. And one example data structure that's very common in this scenario is time partition table, where the new data goes into a recent partition, like today's partition. And then older partitions at some point get dropped, so we can very efficiently expire old data. And keeping the data partitioned in this way keeps the indexes smaller. It means we can very efficiently select the recent data, which is something we wanted. And it has a few other benefits. So Postgres can do this natively, and then there's a few tools to automate it. I mean, they all work pretty well. But you don't want to usually query this data directly if you have a dashboard with a lot of users, because there can be an unbounded amount of data here, and your aggregations can become these super large scans. You could try adding indexes, but you could still have pretty large scans, and every index makes your writes slower, and your writes might need to actually go faster over time. So a common strategy that people use is to pre-aggregate the data in the database. So you could do this manually, where you insert into a pre-aggregated table using insert select, or create a view, or you could use some tools. PGIVM is a very interesting tool that's being developed. There's some others. And the idea is that you kind of summarize your data in these tables, and the dashboard can query the summaries it might still aggregate across multiple summaries, but it only has like a much smaller number of rows to retrieve, usually using an index. So that way you can handle more users. Now, one thing that can happen is that the insert selects that you do to maintain the views get slower over time because you have more data. So one thing you can do about that is to scale out. So this is something people commonly do using Citus, where you could distribute your source data across many nodes, distributed by some column like the event ID. Maybe there's a tenant ID column, maybe device ID. And then the insert select commands into the pre-aggregated tables will be parallelized across all the nodes and all the cores. So if they become too slow, you can add more nodes and they become faster again. But you also need to make very careful decisions around what are my distribution columns? How can I get queries to go to one node and not to all the nodes, because I cannot handle a lot of queries that go to all the nodes. So it's still a tricky problem. And good data modeling is essential. There's nice infrastructure. With Postgres, you get a nice Swiss Army knife, but you have to figure out how to build it yourself to some extent, which views make sense for your application. One thing is that recently vectorized query engines are becoming better at this use case, but we'll discuss those a little bit more in the next workload. So the final workload I'm going to talk about is business intelligence. And so this is where we collect data from across an organization, from vendors, from databases, from telemetry system, from our website, and put it all together and then try to make data-driven decisions by analyzing it. And this data might be collected in a Postgres server or some other database. It might also, but very often nowadays, it's collected in data lakes. So these are essentially files in blob storage, Azure Blob Storage, or Amazon S3 that then you need to kind of go through to find the answers to your questions. So a challenge here is that the data volumes can be enormous, like many petabytes for large enterprises. And the queries tend to be quite complex, and every day, there can be many different new queries that haven't been seen before. And then there's many different sources that you need to combine. You might need to transform, clean the data. So on the plus side, there's typically low concurrency, so not many queries at the same time. So I can dedicate all of the resources of my machines to answering the queries. Now, again, good data structures and efficient use of parallelism are quite essential here. Now, the data structure that's most commonly used for this type of scenario is columnar storage. So the idea with columnar storage is that instead of storing the data row by row by row, which is what most databases like Postgres do, is you take a chunk of, let's say, 1,000 rows, and then you take 1,000 values from the first column, 1,000 values from the second column, and that they're stored adjacently. And when you take values from the same column, there's often a lot of similarity between the values, and so it compresses very well. You can also, with this storage layout, do very fast projections where maybe you only need a few columns from your table for your analytical query. That's quite common, and maybe there's hundreds of columns. So it's much faster if you know, these columns are stored here and I only need to read that part of the table. And finally, perhaps the most important benefit is you can do vectorized execution, which is the idea that once you have this vector of 1,000 values, if you need to do a filter, a where clause, you can first just scan through 1,000 values with a simple for loop, which has no other overhead of it's not doing a lot of function calls. Because if you process the data row by row, you usually have a lot of back and forth with a lot of function calls. And also, when you do those simple loops, compilers and CPU can usually optimize that using special instructions to go much faster. And this can really be 10 or sometimes 100 times faster than Postgres doing the same query, even on the same hardware. And so there is an increasing amount of choice in terms of columnar storage for Postgres. The oldest is Citus columnar. So this is derived from CStore FDW, which is, I guess, really the oldest. And this only does the compression and faster projection, and it stores things just in Postgres. And Hydra is derived from Citus columnar, but adds some vectorization. Timescale has a different approach, but also stores data in Postgres tables itself, Postgres buffers, and it does some vectorization. More recently, there's PG Analytics and Crunchy Bridge for Analytics, which is what I've been working on. And they basically take part of the query execution and give it to a separate executor, Data Fusion in case of PG Analytics and DuckDB in case of Crunchy Bridge. And then they work on Parquet data, and in Crunchy Bridge case, that is in object storage in S3. And object storage is also an important aspect of scaling these types of workloads, because the traditional way data warehouse, where I collect everything in one database, those servers are usually very busy just kind of loading all the incoming data and extracting large amounts of data for other applications, doing all the data transformations that need to happen, and then also doing the queries. But if you move the data into object stores, the big advantage is that a lot of different applications can access them at the same time, can write to it without going through the database server. So now the load and extract and part of the transform can all happen outside of Postgres, outside of the database server, and that can just focus on queries, which is actually quite performant. So in summary, the state of the art for business intelligence is really columnar data formats with object storage and vectorized execution. And there's many analytic stores that use this. You may have heard the names of like Snowflakes and Databricks and BigQuery and Redshift, Athena, like ClickHouse. And so they all kind of follow this approach. But Postgres is now starting to get there as well by taking these sort of third-party open source query engines and embedding them via extensions. So that will make it a lot more suitable for business intelligence and potentially also helps with some of the real-time analytics use cases. So in summary, like we've looked at 3 workload patterns that can become data intensive and kind of different ways to scale them, at least at a high level. So for multi-tenant apps, sharding is generally a good way to go. It can help you escape a lot of performance problems, like your system's under pressure, just add more capacity. That works very well for multi-tenant apps. And for big tenants, you can isolate them to their own nodes in any of the approaches. You mostly need to pick which high-level approach do I want to take, how much like customization per tenant do I need, or how much isolation do I need, or how many tenants will I have. For time series dashboards, partitioning is essential. Pre-aggregation is actually also essential. You can do sharding here as well, but it's not as clear-cut as for multi-tenant apps. You need to think a bit about what are the implications on my data model. So it's always a tough exercise to build a real-time analytics dashboard with a lot of users. And then finally, for business intelligence, like the columnar storage and vectorized execution, even on a single server, actually go a really long way, especially if you're using it in combination with object storage, such that data loading and extracting kind of happens outside of the database. I've personally worked on especially the first 2 problems a lot over the last 10 years with Citus, and now I'm more focused on the third problem, which is also very interesting. And eventually, Postgres is going to get better at all of these. Okay, thank you very much. I enjoyed giving a talk at my first Posette or my third CitusCon, and hope to see you at the next one.